very quick picture about this directivity modification. So this is my 60-second version of it. Could be a 30-minute talk on one slide. I'll try to give you an idea of what I crammed in here. So the idea, this is all from Shrey Shahi's PhD thesis, by the way. So the idea was to take a kind of a classical GMPE. So I'll show you results from the Campbell-Bazornia functional form using all those predictors and same functional form. Add an extra directivity term, and I won't walk through the details of it, except that it's using a couple extra predictive parameters. So here's plan view of a strike slip fault, and specifically it's using a distance from the epicenter to the closest point on the fault to the site, and a measure of the angle kind of between the ray to the site, between the site and the epicenter and the strike of the fault. So a couple extra parameters there, and we fit that directivity term simultaneously with the kind of non-directivity terms. So that influences this function here, or influences the coefficients, because some of the predictive power is pulled into this directivity term instead. So then you end up with kind of an explicit a GMP that has extra predictor variables, and you can do hazard analysis directly with that prediction equation as long as you randomize the S and theta parameters when you do your hazard. But that's problematic for lots of practical reasons. So to try to renormalize that back out, what Shrey did was to take this model and then randomize the rupture geometry. So that's this picture over here on the right. So he would take, for a given magnitude, this is again the strike slip plan view picture. You've got a rupture length, which a little complications because that length's not deterministic given a magnitude and a depth. But let's take a fault length. We'll randomize the epicenters up and down the fault length, and then take all the potential locations around that fault that are at a given distance. So randomizing across those epicenters and randomizing across the potential locations of sites that are the specified distance away. Randomize all those, take an average log, or take an average of this directivity term, and you end up with kind of some average amplification that's back to only a function of magnitude, distance, period, and kind of the regular GMP parameters. So then the question is kind of the residuals from this model versus the residuals from this model. Do you end up with a bigger sigma out of this one? Because then that could be kind of the correction that could be put into a GMP that doesn't have directivity type terms in it. So it sounds nice. It didn't work out quite as kind of cleanly as we hoped. So these are distance-dependent standard deviations from the model at kind of a short period where nothing is happening because this directivity model just doesn't pick up anything, and at a longer period. So in black is the published sigma from the Campbell-Bazornia 2008 model, and then in blue is the kind of refit functional form, but with a distance dependence in it, so kind of in the neighborhood of the published model. And then we've got a couple if we put in the directivity parameters, you end up dropping the sigma comes down a little bit in close, where presumably you're getting a little extra predictive power with these extra geometrical terms. But then if we randomize those and kind of pull that back up, we end up kind of, I think, just back up in the neighborhood of the regular model. So I'm kind of lost in terms of where exactly the sigma went to. Or I go back and forth depending on the day. Either it didn't work, or maybe that's not surprising that we got back to kind of the raw sigma. So we didn't quite get anything real clean out of here.
Can you say why is there these bumps?
So it's just because it's kind of a local regression, local estimate of the. You're talking about like kind of the up and down.
Yeah.
It's just a artifact from the limited data. So there's kind of a windowed estimate of the sigmas. You're pretty sparse in data when you get in close, and when you take this windowed estimate as data kind of leaves the window, you've got what looks like a trend.
And that low on the right at 2 seconds, is that low at 20 kilometers meaningful at all?
I don't think so. I see that the black or the blue one is basically constant, and it's until we move a long ways away from these size bumps. That I maybe believe is partially real, but I don't think resolution on the order of 0.05 here means anything, just because it's pretty sparse in data.
But conceptually, it would have. An ideal result would have been
the
dashed line would have gone
come back up here, right? And you could just take the increase here to plop it back onto the published model, which that distance independent term is much more stable to estimate. Tom?
So could you go back to the previous slide, your directivity model? So did you actually use the epicenter when you
We do to fit the initial model up here, yeah. So you need an epicenter and you need a finite fault. Well, I guess
Yes,
finite
and
fault for it.
then, of course, directivity only occurs when the rupture's in the direction of the slip. So if the rupture's perpendicular to the slip, there's no directivity at all. In fact, it's almost anti-directivity.
Right.
And so Chi-Chi is a good example. Ran a long distance, but no directivity in that. Or the one down south in San Simeon. There are many examples, and if you want to look for directivity in a thrust fault, you got to go up dip. And
Right. So this is the strike slip picture. The geometry is a little different. In principle, it's the same parameterization as Paul had in the 1997.
And so do you put directivity up dip as well? Or?
Yeah. So there's kind of the comparable, length between your hypocenter and your closest distance on the plane, and an angle parameter. Yeah. So it's a different parameterization. I just showed you one to kind of give you a slight picture of what's going on here.
So, Jack, this is Yusuf. So next week, by the way, his thesis will be published as a peer report.
Okay, great. So those are the kind of sigmas that come out of this. I guess the other, maybe as relates to Tom's comment. So when you put this on here, this is kind of only a positive amplification. It kind of adds to the prediction as it's parameterized, but this term will kind of then drop down lower than if you didn't have this on here because some of it's taken away. So one piece that happens is kind of the sigma changes a little bit when you do this, but the other thing that happens is kind of the mean predictions change a little bit. So kind of the non-directivity prediction comes down a little bit, and then this average directivity kind of pulls you back up because some sites have some directivity in them and some don't as you kind of randomize over all these geometries. So just to give you kind of a quick picture, these amplification terms, so they're magnitude dependent because it's kind of a narrow band model that the amplification is period dependent, where the period slides with magnitude. And then it's distance dependent. So I don't think we should look at this for any length of time, but as a function of kind of magnitude, these are 1 second response spectra amplifications from that average directivity. So you kind of, for kind of smaller magnitudes, you get the biggest amplification at 6 or 6.5. And then at like a 7.5 second period, your response spectra, you get a bigger amplification from a long period. So there's kind of these amplifications that are different in functional form than the base model. And so I'm still a little bit up in the air as to whether the sigma didn't come up because we kind of reparameterized it in a different way that kind of fit the data a little better and ate up some of that sigma, or I'm not sure. Shrey is kind of revisiting this again with the NGA2 functional forms and kind of a revised data set. So he's still kind of playing with it a little bit. But as it stands now, I hear some chatter from the back. As it stands now,
His new supervisor said yes, he's going to revisit.
Yeah. So I hope that at some point we'll have a more definitive conclusion about what's going on, but this is kind of numerically what we've seen so far, and I wouldn't stand here and tell you that any of this gives you a clean model to be adjusting for it. I should also mention, I know Jenny's been kind of using our functional form as well as others and trying to reproduce this, and things kind of bounce all over the place depending on how you treat some of your data. It's not a well-defined solution at this point, I would say.
I just want to make a comment, this is Doug Drager, that Tom's correct that for maximum directivity, you need to have the rupture in the direction of the slip vector. But that even in cases where you have, like San Simeon, for example, you will get a weaker directivity, but it's not a non-directivity case.
Yeah. I thought Jenny was going to be here to speak on some of the comparisons. I'd say in general from kind of the studies of this as part of NGOS2 that the sense was the strike slip cases, the various models are in a little closer agreement. For the kind of non-strike slip cases, the models are all over the place, and it's really your model assumptions more than your data that's driving these results. Like depending on how you parameterize this, the directivity effects kind of really slide all over the place in terms of regions where you see directivity. So it's I think not resolved at all in any sort of stable way. So in short, we've thought about it, and I think there is a path through this stuff, but the numeric, I don't feel great with our numbers here, that we've got it figured out just right.
But right now, if we looked at this, it would say, compared to Campbell-Bazorgnia's sigma, there would be no increase, right? I mean, that's how I would interpret
Yeah,
that.
well, and I guess I finish on my thought. So looking at these sigmas, we don't see a difference. Because there are magnitude distance pairs where you get kind of amplifications relative to if you just fit the Campbell-Bazornia model alone, the hazard curves will still go up at long return periods if you kind of use this model or this model, but it's not because you've kind of recentered yourself back on the base model and just have a bigger sigma.
That top model, we've been struggling for years on centering the directivity model.
Right, right. Yeah, and so and I think it points to, does this indicate that we're not centered because there's kind of more cases where we're bumping up than bumping down? Or is there something in the way that we set up the functional forms that's kind of letting it go up more easily than it can go down? We end up with higher amplitudes at long return periods when we run either kind of the top case or the bottom case.
So on your next plot there, no, the next. So what is dash versus dark?
So those ones don't matter. This one was a numerical, just a pure Monte Carlo, and one was he came up with an analytical solution.
Okay.
Yeah. So you can almost analytically solve the integral of kind of randomizing those.
Okay, so that's the change in the median, right?
Right. The thing I don't have a clean comparison for is it's the change relative to the model that was refit with this here, and this is lower than just kind of the as published model. So it comes down in general, and then it comes back up by this, and the two kind of trade off. So you don't come back to just the same predictions as you started with if you left off the directivity stuff. For some magnitude distance period pairs you're high, and some magnitude distance period pairs you're low.
Okay, but I can look at those as an idea of the potential change on the medians, right?
Right.
And if we were going to blur those into a standard deviation, you could still. So if I said, all right, my median's up by 0.15 and I just want to I want to just broaden my sigma to capture that effect.
So the sigma is both kind of the sigma of the residuals
and
plus the
median,
sigma.
right? Because that's we're kind of.
Yeah, that's what you need.
Have you? Yusuf, you're shaking your head no. You haven't? And Bob, you would just say use your model which has the directivity in it, right? So you have it
all taken care of. As a proponent speaking.
But
Right.
I commented.
Go ahead.
The directivity working group Paul's footage recommendation, the punchline was that for a strike slip, the 5 or 4 directivity models are more or less close or reasonable. And then he recommended for reverse fault and bent faults, use more than one directivity model. I'm just quoting Paul's footage in his final report.
Saying that they're widely variable, right? So we need.
So what I'm saying, what just Bob said, that it's included, which is fine, but then you need more than one.
But that doesn't include your model, does it? The TP, babe? What Paul was
Including
does,
this.
yeah.
including this one?
Yeah.
Okay. Tom?
So when you run lots of the forward synthetics, the directivity, the most important thing that comes out is you get these big pulses, velocity pulse in the time domain, and they tend to be fairly localized to specific regions. They're not a really smooth function when you look at them. Some area, and it's not necessarily right next to the fault, sometimes it's off the end of the fault, gets some very large pulse in velocity that can be very damaging to certain kinds of structures. And I have no doubt that those things actually exist. I mean, they should be there and we've seen them, but if you're trying to characterize them with something that's spatially fairly smooth, it might be pretty hard to pick them up. And in a sense, it goes back to the comment I made before about Bayesian statistics. The fallback should be that directivity pulses do exist, and if you don't think they exist, then the data should be challenged to say, pull off at that prior piece of prior Bayesian analysis that says it doesn't work, as opposed to just putting out the data and saying, well, I'm looking for a directivity function.
Fortunately, Paul couldn't be here, but I would suggest that you go back to him and ask him about his opinion about the large variation between the models. I think he made that recommendation about maybe 1 year ago, but a lot has happened since then. So he may have a different recommendation now. So I think, yeah, that's what I want to say. Can you go back one slide? So I don't quite get it. Why do you randomize the hypercenters? Because I'm not quite sure what you try to accomplish or what you try to see here.
So the idea is, if you don't want to randomize hypercenters in your hazard calculation,
Okay.
you're going to do it ahead of time here
Right.
and make a prediction at kind of a.
But why do you put it into your prediction model? Why do you put it into your GMPE? Shouldn't randomization be done when you apply the GMPE?
No, but he would do, the point being, he's gonna take a GMP that doesn't have hypercenters in there and show you how you can adjust the
Right.
sigma or the median so that it gives you the average for a randomized hypercenter case, right? It's just fitting the model in the structure that we're already trying to run.
Right, yeah, so this has got the same predictor parameters as your GMPE, but the functional form is going to be a little different. It's kind of whatever naturally falls out of the functional form from the
Because
directivity model.
alternatively, he could have put hypercenter in there and then
Right.
added another.
But yeah, I mean, if you from the theoretical point, you need to have the hypercenter.
Right. So he tried to do one loop of the hazard calculation before he handed it off to you,
Right.
so that you didn't have to redo it inside this big, huge calculation.
You should thank him for that. Those people that run hazard would be happy to see. All right, I think, thank you.